Hello. We're talking about homonuclear diatomics. So you've probably seen this picture before. This is H2. And we've got a 1s orbital and a 1s orbital, and they are going to be combining together to give you a sigma G, which is sigma Gerata bonding orbital. And there's also the option of a sigma U, which is sigma Ungerata, which is an anti-bonding. So for H2, you've got two bonds, two s orbitals that have positive overlap. You have, because of that positive overlap, you're going to have a region of orbital overlap, or a region of the psi 1 plus psi 2 squared plus 2 psi 1 psi 2. That is your overlap density. MO theory in a nutshell. If, however, this were helium, so helium, then you'd have two in the anti-bonding orbital, which means you'd have, so here's Gerata to where you have, this is upon symmetry inversion, you have the same sign. So this sign and this sign are the same. So if you flipped them or inverted them, then they would not change sign. However, the anti-bonding would look something like this, such that when you added the blue and this green, so this green and this green, there would be psi squared, psi 1 squared plus psi 2 squared minus 2 psi 1, 2. That represents your anti-bonding orbital, which means you have now electrons in a higher than the two separate atomic orbitals, unstable, no bond forms. But that's due to the Ungerata symmetry, such that if you were to invert these two, this one would become this one, which means it would become negative. Okay, so we're now going to combine all of this into how do you convert these atomic orbitals into molecular orbitals via the wave function. So the general rule, actually, first of all, molecular orbitals are formed, come from, I'm going to pause for a second. Cool. Optimizing the time. So molecular orbitals are formed from a linear combination of atomic orbitals, LCAOs. You'll probably see that often. So linear combination of atomic orbitals. So we have H psi equals E psi, the hydrogenic atom. If we know how to represent atomic orbitals, now we're going to add them together, and they're going to have a coefficient that's going to tell us something about that particular bond. A general rule is that all orbitals of the appropriate symmetry contribute to the molecular orbital. It's just easier if I say it quickly and then write it down. So general rule, all orbitals of the appropriate symmetry contribute to the molecular orbital. So I'm going to give you an example. So you already know this. The p orbitals go like, they add together like this, the ones that overlap. An x orbital and a z orbital don't overlap, so you know that they don't form a bond. Okay, so an example of this would be, so this is a 2p ZA. This is a 2p ZB. So this is a 2pz orbital, 2pz orbital. I've got the 2 coming this way as the z-axis. That's what notation I'm using. We're going to go with it. Cool. So this is atom A, and this is atom B. Then I also have 2s orbitals. Literally 2s, two 2s's. So this is a 2sa, and this is the 2sb. All right? Okay, so what we're going to do is we're going to do a linear combination of those. So psi equals the coefficient of A to S, the wave function of A to S, plus the coefficient for B to S, psi B to S, plus the coefficient for A to PZ times the wave function for atom A to PZ, plus the coefficient for B to PZ multiplied by the wave function for B of the 2PZ. Sound good? Okay, so these coefficients are determined to optimize the energies of the energy distribution here. So these are chosen to optimize the energy distribution. So what does that mean? Well, so each of these are going to contribute to, so if we have, so here I'm going to draw a small diagram, whatever it's called, diagram. So here you have molecule A, you have, or atom A, atom B. I don't know if you can see this. So atom A, atom B. And so this is the s orbital, and here are the p orbitals. Of course, they would be adjusted slightly because of orbital mixing. But then you're going to have sigma, sigma star. Depending on the p's, of course, you either have sigma or pi, so on and so forth. So these are going to be lower energy than the p's. Okay, so these coefficients are going to adjust to optimize the energy contribution such that you get the absolute lowest amount of that particular molecular orbital, and likewise the lowest amount of the antibonding molecular orbital. Go team. Okay, so now what I'm going to do, because these are slightly different energies, so this S is going to give me one energy, and then the P's coming together are going to give me a different energy. I'm going to treat them separately. But the other thing I want to take note of is the symmetries are going to contribute the same. So this symmetry and this symmetry are the same. So those are the ones that are going to overlap. This symmetry and this symmetry are the same. And again, you're not going to have a p orbital in the x direction mixed with a p orbital in the z direction. Okay, pause. I'm going to erase. Okay. So I'm going to just look at my 2s. So I have my wave function as my linear combination of my two atomic orbitals. Don't forget, you're going to take psi squared, and that's going to be, oh goodness, Ca2s squared sigma A2s squared plus Cb2s squared psi B2s squared plus now 2 Ca2s Cb2s psi A psi B. Okay, shorthand notation. Okay, so remember, that's your overlap integral. And so how much your overlap integral, then this becomes then, if you integrate all of these, integral big psi squared d tau, this becomes however much your, the extent of your orbital. But then here, this is your s orbital, or not, sorry, your s orbital. This is your overlap integral. And you've got, whoops, you've got the two coefficients. So Ca2s, Cb2s, multiply that by 2. Actually, no, there's not going to be 2 there. Sorry. Integral psi A psi B d tau. What do you know about the two s orbitals of a homonuclear molecule? Go team. Or homonuclear diatomic. These are going to be the same. So that equals 1. So this tells you that you've got those two added together, integral, of course, with this now being that additional component added on to the overlaps. Isn't that neat? All right. Okay. But however, that's not the same when you've got a or an s orbital overlapping with a p orbital. So if you have, let's say this is A and this is orbital B. So depending on how much of an overlap you have, you may or may not get quite a large overlap integral. So I'm going to draw 3 different options. So there's molecule A, and A. So option 1, you have, let's see, So S, which equals psi A psi B d tau, again, that's S over orbital overlap integral, which is that last component because you've got this thing squared and it gives you the cross term. So this is going to be small. Cool. If, however, you have S is big because you have a lot of overlap, okay? And so that means that this contribution is actually going to be larger. And then if you have something that looks like this, where this is your plus and this is your minus, so there is going to be additive. Here is going to be subtractive, which means S equals 0, because what you have here is psi A, psi B, where this is A and this is B, equals 0 d tau, because these are orthogonal. Go team. Sound good? Okay. Spoiler alert. So all of this is based on the fact that these have the similar symmetry. Molecular symmetry or group theory optimizes the fact that you can use matrices to easily solve when these things are 0. Cool? And the idea is that there are certain combinations of symmetries that will always yield a 0 overlap integral. And so you optimize knowing when you'll have a small overlap integral, a large overlap integral, and a 0 overlap integral. Because if you have 0 overlap integral, that means that big psi squared is equal to psi A squared plus psi B squared plus 2 psi A psi B. But if this is 0, that means that you just have 2 separate atomic orbitals. No overlap, no bond. Go team. Awesome. Send questions if you have them. Bye.